notes I'm going to scratch. All right. So, um, geometric and telescoping. Now, they have equal weight in terms of what do you call that, font size in the title, but they should. Geometric is way bigger than telescoping. Geometric is the second most important series there is, and telescoping is just kind of a fun little side note, but it's pretty uncommon. You have to really set up the problem well for it to be a telescoping case. So geometric is the big boy of this lesson. It's super important. You talked about geometric series last year. Geometric, most people think of as the multiplying one, where you get the next term by multiplying by a number, and it has to be the same number each time, yeah? Multiply by 2, for example, right? Now, geometric then is exponential. The question is, how many times did you multiply by 2? The first term, you didn't multiply by 2 at all. It's just a 2 sitting there. The second term, you multiply by 2 once. The third term, you multiply by 2 twice. The fourth term, you multiply by 2 3 times. That's it. All right. Now, this then is geometric. If there's a coefficient, for example, 2 times 3 to the n, it's still geometric. But if there is some or another function, then it's not geometric. For example, if you have 2 plus 3 to the n, that's not geometric. You could split that into 2, and one of them is geometric. We'll talk about that later. N factorial over 3 to the n. Yes, it's got that exponential component, and so it feels like maybe geometric, but because that factorial, not geometric. These are not geometric. You follow? All right. Now, students want to call it, because it's a multiplication pattern, they want it to be called a common factor. The common factor is 2. That's not what you say in geometric. You say common ratio because it's really not so much what did you multiply by, but if you divided any term by the term before it, it's a common ratio. The ratio of 4 to 2 is the same as the ratio of 8 to 4, is the same as the ratio of 16 to 8. The common ratio is 2. There's a ratio in common. Common ratio. That R, a common ratio is called R, right? If there's a common ratio, then it's geometric. I have in my notes, I want you to compute the first 3 common ratios, second to first, third. Let's just blow it off because you wouldn't be doing that in the homework anyway, and just say, is this geometric, yes or no? Yes. Multiplying by what each time? 1/4, all right? So you'd say yes, R is a 4. What about the next one? Are you multiplying by the same thing every time? What this times what equals -3/8? -1/2. You do that again, would you get 3/16? And if you do that again, would you get -3/32? So because you seem to be getting the same thing, or what you would expect each time, you say yes. And R is -1/2 in that case. What about the next one? What did you multiply the top by the first time? This is times 2 over 2, but this is times 1.5 over 2. That is not geometric because it's not the same ratio. Follow? All right, and then the last one. Does it feel like it fits the geometric pattern, exponential only?
Yes.
It is. What's the common ratio? Is it 3 or 1/3 or negative 1/3? If you're not sure, do a few terms. When n equals 1, you get a positive 1 over 3. When n equals 2, you get a negative 1 over 9. Then a positive 1/27. Students, at least starting, you'll get so that you'll look at the summation and you'll see it all. But starting out, some students feel like it's easier to look at the actual numbers, this expanded form. And then, can you say, is it geometric?
Yes.
Yes, and what's the common ratio?
Negative 1/3.
Negative 1/3. All right. So, that's the big idea starting off. How about, actually, never mind, we're not going to do that. We don't need to be able to do that. All right. Now, yesterday we talked about how if you add infinitely many terms, it's kind of hard to converge to add infinitely many things, and the only way it's going to even have a chance is if the terms are getting smaller and smaller. And it's actually not even enough that the terms get smaller and smaller and go to maybe 1. This wouldn't converge. For example, if you said 3 plus 3.1 plus 3.01 plus 3.001, do you agree those terms are getting smaller? And if I added infinitely many of them, would I get a finite sum? No. I mean, it doesn't matter that they're getting smaller. I'm going to get infinitely many 3's. That's not going to converge. So it's not enough just that they get smaller. They have to get smaller and go to 0. If the terms don't go to 0, the series diverges. Done. End of story. No chance. If the terms do go to 0, it has a chance. Now, in a geometric series, imagine a multiplying pattern. Start with any number, 5. What would cause me to get smaller or go to 0? If I multiply by, must be, give me a theory. R must be a fraction, okay? All these are common responses every year. Fraction, not quite enough, because what if R is 3 over 2? Will they get smaller? I mean, that's a fraction, I think they'll agree. But do the terms get smaller? No. Okay, so it can't be just a fraction. What else? I heard somebody else say less than 1. Less than 1, or less, that is redundant. Less than 1. Okay. What if R is negative 2? And the series is 5 minus 10 plus 20 minus 40. What do the sums approach? They would go negative 5, then 15, then negative 25. Those aren't going to spiral in. Those are going to spiral out. That doesn't work either. So, absolute value, and I heard Emma's also. It doesn't have to stop at 0. It can go negative, but where would it have to stop on the negative side? You're right. Where would it have to stop on the negative side? It couldn't go below. In order to get smaller, you could multiply by negative as long as you stopped at negative 1. Okay, so it needs to be either absolute value of R is less than 1. In other words, in between that negative 1 to 1 region. Those numbers, when you multiply by that kind of number, you get a smaller quantity, and the sign doesn't really matter. As long as the number, quantity, the absolute value gets smaller. Are you following? All right. Now, again, I would develop this, and if I were your pre-calc teacher, Ms. Cannon probably developed it for you. You can, it's crazy, but you can actually get a formula for an infinitely large thing by elimination of the formula with a form of itself, and you cancel out a lot of terms. Did she show you that last year? Okay. In the interest of time, I'm going to simplify it down to an infinite geometric series. The sum can be found as long as this category, this condition is satisfied. If the common ratio is between negative 1 and 1, then the formula for the series is A1 over 1 minus R. Now you probably learned the finite formula also. That's actually a bit uglier. That's harder. We don't even sweat finite here, we just do it. All right, so this is the clean one. Are you with me? Please, I beg you, don't be the knucklehead. Every year there's a knucklehead. In fact, several knuckleheads. Don't be the knucklehead. Check R first. I guarantee you, I'm going to put a problem on the test, and it'll be this. 1 plus 2 plus 4 plus 8 plus 16 forever. And student A, the knucklehead, will say, oh, it's geometric. The sum is A1 over 1 minus R. What's A1? 1. What's the common ratio? 2. And so they would assert that that answer is -1. Now they're locked into their little formula memorization, and they have lost all common sense, because even a 3-year-old, well, maybe not a 3-year-old, but even a 7-year-old could say that's stupid. 1 plus 2 plus 4 plus 8, positive numbers, getting bigger forever, becomes a negative number? How can that be? Surely not. Okay? And it's because this person is an idiot. They didn't check the condition was met. You must first say, does R satisfy the condition? Okay, it does, so now I can use the formula, and only then can you use the formula, all right? Check the condition first. So, for example, this bad boy, you know that R is, what's R? 3. That's not less than 1. So this series, this S stands for the infinite series, diverges. It is an infinite sum. It fails to converge. Don't even try to use the formula. It's not applicable. This, what's the common ratio? What are you multiplying the top by? 1/3. The top is times -3 each time. Do you agree? And the bottom is times 2 each time. That is not less than 1. At least the absolute value of it isn't less than 1. So that diverges. Because that's negative, that actually, the sums would bounce back and forth between positives and negatives and spiral out. It would not converge. How about this one? What's the common ratio? Is it 2 times 2/3 or just 2/3? If you're not sure, do a term or two. Just 2/3. You are correct. Good job. Are you speaking for Sam there, or? Oh, good job, ladies. All right. So R equals 2/3 is less than 1, so the condition is satisfied. If that happens, then you use the first condition, go on to the second round, is find the sum. For A1, you need to actually be careful and plug n equal 3 into the function, and that's how you're going to find A1. What do you get for A1 when you plug n equal 3 in for your first term? 2 times, what did you say? Oh, you said 60. I'm with you. 2 is there. 2 to the third is 8 over 27. So I see where you're saying 16 27ths. I agree. 16 27ths up there is true. What's the common ratio? 2/3. That would need to be simplified. So we have 16 27ths. The denominator is 1/3, but when I flip it up, it's 3 over 1. So the sum of this is 16 9. So if I busted out my calculator and added terms and kept adding a term, it would start approaching the limit of 16.
So that 2 does nothing for us? Like that's the exact same as the sum if the 2 wasn't there?
The only effect is on the A1. It did show up here. It affected A1, but it didn't affect the common ratio.
Okay.
Yeah. So it is important. You can't blow it off altogether.
Okay.
All right. The last one is a power series. We talked about this yesterday. The common ratio is what? Almost. -x, yeah. -x. Now, who's to say if that's less than 1? This would actually converge if absolute value of x is less than 1. So you would actually, you could get basically a picture of this, and any x in here for any x you put into that function, you would actually get a finite number. So this would actually be a problem of many infinite summations. I could plug in a half and get a sum and plot that sum. And I could plug in a 0 and plot that sum. So this would be a lot of possible infinite sums. But they would only exist here. Anything outside this region would be infinite, and there would be no graphing point there. You follow?
Yep.
Okay. Talk about this guy. Now, we're going to do this on 2 levels, Algebra 2 and Calculus. Do you have it? Yeah. Okay. Do you remember doing this in Algebra 2? It goes like this, the Algebra 2 way. Back in the day, the goal is to make this a fraction. This is a rational number. They call it a rational number because you can make it a ratio of two whole numbers. If you call this number n, and let's call it a bunch of 2, 3, 4s forevermore, then back in the Algebra 2 day, you made this a fraction by canceling out that infiniteness with more infiniteness. Now, a stupid thing to do would be to say, oh, so you could just subtract it from itself. Well, yes, I suppose you could, in which case you'd get 0 equals 0, which is true, but not very informative. Instead, you take this and tweak it a little. How could you shift it over in power so you could get a new 2, 3, 4? Make it a decimal, so, or a bigger number. So I can either multiply or divide to shift it over 2, 3, 4. Let's multiply by, what should I multiply by to shift it over 3 places so I get a new 2, 3, 4? 1,000. Is that always 1,000, or is that a product of this problem? This problem. What in this problem means 1,000?
There's 3.
3 repeating. If it was 3 repeating, you multiply by 1,000. If it's 2 repeating, you multiply by 100, so on. So this would be 234.234,234. And I could combine those by subtraction. If I subtract, let's assume we take the smaller one away. So I get 999n equals 234. So n, the integer of fractions, is 234 over 999. Okay, now if you do this in a calculus way, then you're going to make it a series. Break it up into every 2, 3, 4 separately. The first two, actually, let's write it. It helps to write it expanded first, so we have that to look at. So write me a couple 2, 3, 4s. I wrote a few. Right? The first 2, 3, 4 would go through the thousands place. The second 2, 3, 4 would actually be after 3 zeros, then that new 2, 3, 4. This guy would be after 6 zeros, then 2, 3, 4. If I line those all up decimal-wise, they would give me that same 2, 3, 4. Do you agree? Is this geometric? Geometric with r equals 1 over 1,000, which I normally would prefer fractions, but in this case, we'll use those. All right. Now, if it's geometric, I think you'll agree that that's definitely less than 1, so it converges.
Yeah.
So the formula, a1 over 1 minus r, is, what's a1? 0.234, or 234 thousandths. And the common ratio we just said is 1,000. That's 0.234 over 0.999. If we multiply top and bottom by 1,000 to clear the decimals, then we get 234 and 999. And obviously that's the same.
Why would you do it that way?
Who's to say what an easy way is?
I'm saying that's the easy way.
The other way?
Yeah. So I can use that one.
Yeah, unless it says, if it says use a series, then you have to use a series. All right, now, that said, with series knowledge, what this wouldn't do is prove that an A is an F. With series, you could prove an F is an A. Would you be interested? Oh, I already know. Don't look over here. This is, okay, I meant to do it on the board here. So let's prove an F is an A, shall we? I will prove that 59 is just as good as 100. In fact, it's the same, yeah? All right. Now, you tell me if you can spot my flaw in logic. I'll start with something I think you'll agree is true. Yes? Do you agree that's true? Okay. Do you agree that 59 is equal to 59 plus infinitely many zeros? Okay. Do you agree that 41 minus 41 is 0? So I assume you'll agree with that every time I do that, yeah? Okay. Do you agree with the associative property of mathematics, which is to say that when you're adding, the order in which you group does not matter. If I add these, this is the same as this. That's the associative property, yeah? Now, you could say then that these parentheses, I could dump them. Yeah? Likewise, I could instead add these. Yeah? What do you mean no?
I just don't think that is an A.
What? You don't think I can put parentheses around a sum?
I just feel
So
like
you're arguing that this is not the same as that.
No, I'm down with that part. I just feel
So what's the difference? If you say 41 is different than 2, they don't behave the same.
okay, what?
Okay? So what is this equal? 100, and this? So therefore, 59 equals 100, right?
No.
Right. Oh. Right. It does. 59 equals 100. Okay. Now that actually, you're right in the exact same place that you are not allowed to do this. For infinite series, you cannot just throw parentheses in no place. There are rules to where you can put parentheses. But yeah, it's kind of a fun argument. Your parents won't know that infinite series parenthesis rule, so try that. All right. Next, in order to introduce the next idea, we need to watch a 30-second clip. Okay. Now, that's not your normal telescope. That's a great movie. That's not your normal telescope. What's the name for that kind of telescope? Oh, that's a similar. That's a collapsible telescope. It's meant to collapse onto itself, yeah, into one small piece. That is the key to this lesson here. A telescoping series collapses. Write that down, please. It will collapse. Oh, I spelled collapses wrong. It doesn't have two S's in it. Collapses. Okay? Now, how it collapses, or proving how it collapses, that's the meat of it. The numerical part of it, you'll get the points for that. You'll probably know, oh, it's going to be 1. The proof of it, that's the little more work of it. That's the stinker of it. All right, so check this out. Would you take a look at this? Now, whether you know it or not, that's a telescoping series. If you put in n equal 1 for A1, actually I'm going to call this A1. A1 is not just one term, it's 2. 1 over 1 minus 1 over 2. That whole thing is A1. A2 is 1 over 2. When I put a 2 in, I get 1 over 2 minus 1 over 3. When I put a 3 in, I get 1 over 3 minus 1 over 4. you know, you need to put the parentheses in, students just find it easier to separate one from the other if you did. All right, now, it says through A4, sorry, I should have had one more term before I build. A4, then A4 is 1/4 minus 1/5. Do you see where I'm getting those terms? Okay. Now, we talked, remember yesterday, oh, here's the tell, I guess that's right there, never mind. Remember yesterday, an infinite series converges if the partial sums approach a limit. All right. So in order to investigate that, let's look at the partial sums. The first partial sum, which you call S with the subscript of 1. Now, don't think that 1 means just that. 1 means all of A1. And so that's 1 minus a half. Write yourself a note, please. It'll explain, it'll mean more in a second, but only simplify collapsing terms. And by that I mean do not simplify. You don't want that to be a half. It doesn't help you. It's counterproductive to simplify that. Leave it alone. S2. When I go through the first two terms, you can see that the halves, negative 1/2 and 1/2, whoosh, right?
Yeah.
And if you whoosh, then you're left with 1 minus a third. If you go through the first three terms, then whoosh, 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 and you get 1 minus a fourth because the halves and the thirds collapse. And the fourth partial sum is whoosh, whoosh, whoosh. So 1 minus 1/5. Now surely, the more and more terms you add, the more terms collapse away. You're always going to get two terms, 1 and something, but that something gets smaller and smaller and smaller. You could find a general formula for the nth partial sum by looking at that pattern. What's always there is 1. The 1 is constant. It's not related to the term number. So I just write that down. Same with the subtraction, same with the numerator 1, same with the fraction part. What does change is the denominator. The denominator, what is the denominator relationship to the term number? Well, look back here. 1, first term, there was a 2. Second term, there was a 3. Third term, there was a 4. Fourth term, there was a 5. So the nth term is n plus 1. That denominator is always 1 more than the term number. All right. Now then, if we use this idea, if I want to prove the infinite converges, I need to take the limit of the partial and show it comes out to a finite number. Partial formula. The limit as n goes to infinity of 1 minus 1 over n plus 1 is, well, as n goes on, what happens to that thing being subtracted? A half, a third, a fourth, a fifth, it goes to 0, and it approaches, therefore the sum approaches 1. It's an infinitely big number of terms, but it goes to 1. Now, if you're like the last class, you say, oh, I see everything collapse, but what about the last term? To which, of course, you say, that's stupid. There is no last term. It's infinite. What's the last term? The infinite number term? The infinite plus 1? That doesn't mean anything. There is no last term. They are canceling now. They are canceling forever. They'll cancel after you die. They'll still be canceling. Okay? But they always cancel. Okay. Now then. The hard case then is to come up with a formula. We're going to do the second and the fourth. They're the good instructive problems. So we'll do those here. To find a telescoping a telescoping collapses, first expand to, I don't know, maybe A3 or A4-ish. So in this one, A1 is, be careful, look at the starting index. What's A1? 1/3 minus 1/4. All of that is A1. A2 is 1/4 minus a fifth. A3 is a fifth minus a sixth, and A4 is a sixth minus a seventh, dot, dot, dot. Depending on the complexity of the series, you might not need that much, right? Second, find through S4. And again, that's ish. You really just go until you start to see a pattern. S1, 1/3 minus 1/4. Only simplify the collapsing terms. What about S2? 1/3 minus 1/5. The fourths collapse. What about S3? 1/3 minus 1/6. Now you, like I said, you go until you see the pattern. You might say, I see it, and that's fine. If you don't see it, then you should continue. I'll explain that in a second. Okay, write a formula then for the general partial sum. What is a formula for the any partial sum? Any partial sum. 1/3 minus 1/n plus. Okay, so here's n, so tie it to n. It looks like that denominator is n plus 3, all right? Draw those little arrows to tie the subscript or the sum number to what the denominator is doing, all right? Finally, take the limit as n goes to infinity of your partial sum. The infinite sum is what the partial sums approach. As n goes to infinity, 1/n plus 3 goes to 0, and so the sum collapses and approaches nothing. Okay, would you try the next one on your own? But I'll warn you, be persistent. It's going to be a little wide. How we doing? Really? Okay, so check your partial sums. 1 minus the third for the first one.
Yeah.
1 minus the third plus a half minus a fourth for the second. Nothing collapsed. The third one, something starts to collapse. The third drops out. It's a 1 plus a half plus a minus a fourth minus a fifth.
Yeah.
Okay? You're definitely never going to see a pattern until you start seeing collapsing. All right? So don't even, if I didn't see anything collapse here, I wouldn't even waste my time. I would just keep going until it starts collapses. 1 plus a half, then the third and the fourth drop out. You have 1 plus a half minus a fifth minus 6.
Yeah.
So at that point, it seems like the 1 plus a half, they're always there. So in the general formula, they're still.
But why isn't it in the first one?
Okay, so good question. Is this going to even work for the first one? No, that's a good question. Let's continue on. Forget the first one, and let's just plow ahead. What about the things that change? These second terms seem to vary, and so they probably should tie to the counter. What is the first fraction that's subtracted? 1 over n plus 1 and 1 over n plus 2. So your question then is, well, what the heck? What about the first term? The first term would be n equal 1, yeah? That would be 1 plus a half minus a half minus. Still, it doesn't look like it would, but it does. Okay. So what's the infinite limit? As n goes, as you add more and more terms collapse, and it starts to approach just the two that don't collapse, which is 1 1/2 or 3/2, whatever you prefer. You follow? All right, and then the last case is sometimes it's not set up all pretty, princess, for you. You have to make it telescoping so it collapses. The whole idea of which is a term minus a term. I don't have a term minus a term here. How do you reckon I make this telescoping? How do I make it a term minus a term? I heard a lot of. How do I make a fraction like that into two fractions, added or subtracted? Partial fraction. All right, so 2 over n times n plus 1 equals a over n plus b over n plus 1. 2 equals n times a times n plus 1 plus b times n. Let n equal, what do you want to let n equal?
0.
0, okay, and negative 1 I heard, that's true also. Let n equals 0, and I get that a is 1/2 or 2? 2. And n equals negative 1 means b is negative 2, I heard, yes, that's true. Okay? So this infinite series we were given, infinite series we're given is the same as the separate 2 over n minus 2 over n plus 1. All right, now you try writing or proving that it converges to a finite sum. get a partial sum pattern like I have here? What's your nth partial sum formula?
2 minus 2 over n plus 1.
2, and I agree, that works. And then what do I do after that? Take the limit to show the partial sums converge to a finite sum. You take the limit as n goes to infinity, this goes to 0, and the sum approaches 2. Last but not least, look at the next one. That definitely does not feel like telescoping because it's not a subtraction of 2 terms. How could you make the last one a subtraction of 2 terms? Split the natural log. Yeah, use natural log rules. And natural log of n minus log of n plus 2. Now, eventually you'll see that problems like this guy here, this one up here, where it was a bigger pattern, we had to go further. That was a result of these being 2 apart from each other. When these are 1 apart from each other, it collapses quickly. The further these are apart from each other, the longer it takes for collapsing to happen. It'll be after several. So these were 2 apart, it took a while. If this had been n and n plus 3, it would take even longer. These are 2 apart, so you would have to do lots of cases before you saw the collapse. You with me? Okay, cool. That is that. Questions on 116 or the logistic homework I just handed back, whichever you like. Or should we just do some off, say, forget 116 and do some off tonight's homework on tonight's?
What's the homework?
Last night's or tonight's?
Tonight.
Tonight's?
Yeah.
Let's get 6 or 9 done on tonight's homework. What do you say?
Like,
6 problems. Yes, I mean 6 problems.
what?
Okay, so 4 is this. 5 is this. And 6 is this. The question is, show that the sequence, not series, sequence, which is the terms, converge or diverge. How do you show the sequence converges or diverges? That we've been doing for a long time. Take the limit of the terms. Yeah, the limit of the term generating formula. As n goes to infinity, what do those terms approach? Not the sum, the terms. 0. So we conclude, because that's a finite number, we conclude converges. What about the limit of 3? We could put that together. As you took 3/5 times itself more, 9/25, 27/125, 81 6/125. Those go to 0. You can also say this converges because it's geometric. Oh, that's a sum idea. Never mind. Forget that. We'll come to that in a second. Converges, yeah? What about the last one? Converge or diverge? Diverge, because the top goes faster, this goes to infinity, and so it diverges. All right. Now let's talk series. Number 7. Says, does it converge or diverge? And if it converges, find its value. What kind of series is that? It's geometric. When you see that exponential and coefficients, okay, it's geometric. It's geometric. What's the common ratio? Is it 3/4 or 1/4? 1/4. You're only multiplying by the 4 each time. The 3 just stays 3. It doesn't change. So the common ratio is 1/4. Does that satisfy the condition of less than 1? Yes. So we state that it converges. They also said if it converges, find the sum. How do I find the sum if I have an infinite geometric series? Sum formula A1 over 1 minus R. What's A1? 3/4, and the common ratio. Sam, what's the common ratio? 1/4. So what is 3/4 over 1 minus 1/4? Corinne? Ah, zoned out, got you. It's 1, yeah, it's just 1. Or I freaked you out because I actually finally called on somebody else besides Emma. Lauren was always talking. All right, 8. Well, I appreciate it. 8. How about doing that one on your own? It's 3 to the n over 5 to the n. The question again is, does it converge or diverge, and why? And if it converges, find the sum. If it diverges, you don't find the sum. That's ridiculous. It doesn't have a sum. This is geometric. What's the common ratio? Does that satisfy the condition for convergence?
Yep.
What's A1? And what's the common ratio?
3.
What's 3/5 over 2/5? Okay. Last but not least, 9. 5 to the n over 3 to the n. Is it geometric? The answer is yes. What's the common ratio? 5/3. Is that less than 1? It is not. So it diverges. These terms are going to get bigger and bigger. Then you're trying to add them. That's not happening. Okay. Do we have time for one more? That's pretty much it. Well, we got 6. That's a start. All right.
Knock one more out.
Knock one more out.
Let's do 10.
10. All right, go overachiever. Just go get her. 10.
Actually, on the ground, not to do 10.
Oh yeah, 10's not going to happen. We could do something else. Never mind. No. All right. I keep getting a whole bunch. All right. Okay.
I think Julia's okay with that because
Yeah. Look at this. You want to go crazy with that? Yes, exactly. I knew you. The minute I did that, I thought, you need to freak out. I think this is AB. Those will serve my best. Am I right? All right. Have a nice weekend. Oh, yes, you're turning. Yeah, you're turning at 116. You betcha, baby. You betcha. Questions? I have answers. I'll be here a little after school. Have a nice weekend.
Thank you.
Thank you. Emily, what are you guys doing after school? You and her?
Well, I think I was gonna go to a swim meet, but it's not bad. I don't wanna. That doesn't know. I might just go home, honestly.
They don't
Harper
cancel swim meets.
definitely doesn't have any good plans.
She doesn't have to. You guys aren't going to girls' basketball?
I don't think so. You just had your movie.
Do you guys go to basketball today or just
I
maybe?
don't want it to. No, football was tomorrow.
Oh,
That's tomorrow.
okay.
We're going to that.
So
I don't
we're
know.
going
I'll
on
keep you updated. No, Mom and I go to Toledo. She made it right.
She's in the army. There it is. Got it?
like
Yeah,
that's what I do over the weekend.
exactly.
All the other stuff I
Yeah,
have
it's
to
fun.
do.
So yeah, ukulele or a job or
Yeah, all of that plus more.
yeah, so many.
I have a really busy weekend. I'm like,
Really?
oh,
Oh, 3 days though. At least you can stretch it over 3 days.
yeah. It's just gonna be like I have to do all my homework on Monday because I haven't been time for the rest of the weekend. So I'm like, great.
Well, have a little fun in there. Keep it all work.
At least it'll be. I have the entire day on Monday to do it instead of just time
A couple
after 3
hours
o'clock.
after school, or 11 o'clock. Yeah, that'll be a relief. You work on your homework when it's still light out. You don't even know what to do. Oops, I've been recording this stuff.